Hi students, now we are going to derive an expression for the magnetic field due to a long current carrying solenoid. So in this picture we can see a solenoid which is kept in the horizontal direction. This solenoid consists of so many circular turns. So you have to imagine that a solenoid is having so many circular turns. Whenever we wind the wire over the solenoid, the wire is going inward through these points and the wire is coming outward through the points at the top. So I have wound the coil by penetrating this wire inside the board and taking it outside the board at the top points. So this is a section of the solenoid. So these X points are inward through which the wires are going in. And these circles are the points outward through which the wires are coming out. Now let capital N denote the total number of circular turns of the solenoid. And let capital L represent the total length of the solenoid. So the total length is capital L. And let I be the current flowing through each turn. Normally each and every turn they are in series only. So the same current only has to flow in each turn. But in our Ampere circuital law, if I ampere is the current flowing through one turn, what should be the current flowing through n turns then in an Amperean loop? If the Amperean loop contains a capital N number of loops, then the net current is equal to n times the current flowing through one loop. This is the concept I am going to use in the derivation. Okay, now this small n equal to capital N by L is a number of turns per unit length, that is called as turns density. Okay, now we want to derive an expression for this magnetic field B along the axis of the solenoid. So along the axis of the solenoid the magnetic field is uniform. So I have represented the uniform magnetic field by parallel lines. There is no magnetic field outside the solenoid if it is an ideal solenoid. Moreover, here the length of the solenoid is comparatively greater than the diameter of the solenoid. Okay. Now I am going to consider an Amperean loop. An Amperean loop, say for example this rectangular loop, namely small a, small b and small c, small d. So A, B, C, D is a rectangular Amperean loop I have assumed. You can see that some portion of this Amperean loop is enclosed inside the solenoid and some portion of the loop is outside the solenoid. First that has to be noticed. Now generally if I apply Ampere's circuital law, okay, for this closed loop A, B, C, D, there are four sides A, B, BC, CD and DA. These are all called line elements. Line elements are vectors. Therefore, AB, this line element AB is along the field B. Another line element BC is perpendicular to the field B. The line element CD is out of the magnetic field B and the line element DA is once again perpendicular to the magnetic field. So the Amperean loop contains four elements, DL elements. AB along the field, BC perpendicular to the field, CD outside the field and DA again perpendicular to the field. So what is the closed integral B dot DL for this Amperean loop? So from Ampere's circuital law, closed integral, okay, closed integral B dot DL. So this is a B dot DL is equal to mu naught times the net current enclosed. So what is the current enclosed by the Amperean loop? So this closed integral B dot DL has to be applied for four elements, namely AB, BC, CD and DA. So I am going to take the left hand side as a closed integral for the loop A, B, C, D. Can you see here A, B, C, D? Okay, that is the Amperean loop. So for the entire loop, if I apply B dot dl, this will be equal to closed integral for the element A to B. For A to B, B dot dl. So the first term is A to B plus the second term is closed integral B to C. And for that I have to find out B dot dl. And the third element closed integral C to D. This is B dot dl. Plus the fourth term is D to A, closed integral B dot dl. So in this, the left hand side is having four terms, one each for each line element. So I will write now closed integral. Now the second term, third term and the fourth term are going to vanish here. So I will explain these three terms first. So look at the second term here, closed integral B dot dl from B to C. You see here B to C. So here closed integral B to C, B dot dl. So B dot dl, this is equal to, now here the magnetic field vector B and the line element vector are perpendicular to each other. So here theta is equal to 90 degree. So this is now becomes a closed integral B into dl into cos of 90 degree, and that is equal to 0. Okay students, so cos 90 is equal to 0. Now similarly I will take the next term, the third term. The third term is from C to D. So this is from C to D, the dot product B dot dl. Look at the element C to D here. C to D is a line element outside the field where there is no field at all. So here there is no magnetic field. Therefore this term is equal to 0 because B is equal to 0. Okay. Now we come to the next, the fourth element, namely D to A. So what is the closed integral D to A? D to A, closed integral B dot dl is once again you see here D to A is perpendicular to the magnetic field. So here also theta is equal to 90 degree. Therefore this is equal to B into dl into cos of 90 degree. That is equal to 0. So did you understand that in this right hand side the second, third and the fourth elements, okay, the dot product of B dot dl for the three elements namely BC, CD and DA become 0. So only one element is remaining, that is integral A to B B dot dl. Okay. So now the right hand side I am going to see here mu naught times the current enclosed. Now current through one turn, okay, that is current in one turn is equal to capital I. Therefore net current is equal to the total number of turns n into I. So net current is equal to what? N into I, is it not? N into I. Then closed integral B dot dl, closed integral B dot dl for this ABCD is now equal to, this is now equal to only the first term is remaining. So this is first term is what? A to B, and this is now field is uniform, and the angle between B vector and dl element vector is along the field B. Therefore here theta is equal to 0, so cos 0 is equal to 1. So B into integral of dl, okay, from A to B. Now here the element is AB, which is shown in the picture as small. You imagine what will happen if the Ampere loop is extending from the left end of the coil to the right end of the coil. It is arbitrary. Any value we can assign for this element AB. Suppose if the length AB is equal to the total length of the solenoid, then also the turns ratio will be the same. Therefore, this integral of dl, I can substitute either AB or the entire length of the solenoid also I can substitute. It is our choice. So, this is now equal to B into the total length of the solenoid itself, that is equal to B into L. B into L. Okay, students? So, now you will see here, this is the net current. This is the net current. For example, I will say this is equation 1 and this is equation 2. So, I am going to apply this in the basic equation of the Ampere circuital law. Therefore, in Ampere's circuital law, closed integral B dot dl is equal to mu naught times the net current enclosed. So, instead of integral B dot dl, I am going to substitute equation 2. So, left hand side will become B into L. This is equal to right hand side is mu naught into, instead of I net, I am going to substitute what? N times the current I. So, this is equal to what? Capital N into I. Or what is now B equal to? B equal to mu naught into N by L into I. So, what is already N by L? If this L can be taken as capital L also. So, here capital L I have taken means here also I can substitute capital L for the total length of the solenoid. So, this ratio of N by L is equal to what? The turns density small n. So, I am going to substitute here small n. Therefore, okay, therefore, B is now equal to mu naught into small n into the current I flowing through each turn. So, this is the final equation number 3. So, this is the required equation for the magnetic field due to a long current carrying solenoid. Okay, students. Now, you see that B depends on the turns ratio. Turns ratio is a constant for any solenoid. And the current I also is a constant. Okay. Therefore, B is constant. That means it is a uniform magnetic field along the axis of the solenoid. Now, if you have assumed air core solenoid means on the right hand side the term mu naught will come. Suppose if you place a soft iron or any other ferromagnetic substance, then for any medium, okay, for a medium placed inside the solenoid, this B will be equal to mu R into mu naught Ni, where mu R is the relative magnetic permeability. Already we have introduced this in the previous derivation. Mu R is equal to mu divided by mu naught. So, what do you understand from this equation 4? Okay, when any ferromagnetic substance is introduced inside the solenoid, its magnetic field strength increases. Okay, students, I hope you must have understood.